Everyone, welcome you all to week 7 problem solving session of the course Introduction to Group Theory. I'm Priyanka Sharma and I'm your NPTEL teaching assistant for the course. In this tutorial, we will study about the isometries of the plane R square. So to study isometries, first we recall some basic terminology. So R square, which is isomorphic to the uh, complex plane C. So this is actually uh, like the collection of all these tuples x comma y, where x and y are coming from R, or it can be either represented like x plus I y. So how to define the inner product, which is actually the dot product in R square. So suppose we have two elements, u and v in R square. So obviously u and v of the form of some tuples. So if u is a comma b and v is c comma d, then to define u dot v or the inner product of u and v, what we will do, we will first get the product of first tuple, that is a and c, and then we add the product of like second coordinate of both u and v, that is a plus c plus b plus d. So this will be the inner product of u and v. Now, how to define norm in R square? So norm of some element, say u, this will be defined like this. That is the square root of a square plus b square, where u is the vector ap. Equivalently, we can say that norm of some vector u, this will be the square root of the inner product of the vector by itself. Now, how to define the distance in the plane R square? So suppose we have two elements, say u and v. So how to define distance between u and v? This is basically the norm of this, the difference, that is the norm of u minus v. Clearly, this will be the square root of a minus c square plus b minus d square. Now we come to define the isometry of R square. So isometry of R square is actually a map from R square to R square, which satisfies this condition. That is, the norm of hu minus hv is same as the norm of u minus v for all u and v belongs to R square. That is, isometry is a norm preserving map, or we can equivalently say that this is a distance preserving map. We can equivalently say that distance between hu and hv, this is same as the distance between u and v for all u and v belongs to R square. So if the map H satisfies this condition, then we say that this is an isometry of R square. Now, what is a linear map? So a linear map on R square is a map which satisfies these two conditions. That is, the addition is preserved. That is, t of u plus v is t of u plus t of v, and t of c u, where c is some scalar. This is coming from R. This is same as c t u, and these two conditions are true for all u and v belongs to R square and for all c belongs to R. In that case, we say that the map T is linear. Now, this one, E1 and E2. This is the notation for the standard basis of R square. And here we take E1 as 1, 0, E2 as 0, 1. So what is the basis in R square? It will be a collection of two elements of R square which are linearly independent, and they generate or they span every element of R square. That is, for each V belongs to R square, there will be uniquely some X and Y belongs to R square such that U can be written as X E1 plus Y E2. It means every U belongs to R square can be written in terms of E1 and E2, where E1 and E2, they form the standard basis of R square. This is an important result that a linear map can be uniquely determined by its action on the standard basis elements E1 and E2. That is, if we know what is the value of TE1 and what is the value of TE2, then we can get what will be T of X, where this X belongs to R square. And how to do that? Suppose like we want to find the image of this element V. So V can be written as X E1 plus Y E2. Then TV, this will be X TE1 plus Y TE2. Here actually X and Y, these are coming from R. So we can apply this second property, and for like to separate the action of T on E1 and E2, we can use the first property. So if we know how a linear map T transform E1 and E2, then we can find its definition, we can find its form for every element of R square. Now, what is orthogonal basis? So first we need a basis, say U comma V, this is a basis in R square, then this will be said to be orthonormal basis if the norm of every basis element is 1, that is norm of U and norm of V, they are 1, and inner product of U and V, this is 0. So in this case, we say that U and V, this pair, form orthonormal basis for R square. Now, if we have an orthonormal basis, say U and V of R square, then for some given omega in R square, this omega can be written as C1U plus C2V for some C1 and C2 in R, and this U and V, these are orthonormal basis elements. Here, C1 will be omega dot V and C2 will be omega dot, C1 will be omega dot U and C2 will be omega dot V. So if we substitute these values, then we can find the form of omega, which is omega dot U into U plus omega dot V into V. Now we want to classify the isometries on the plane R square. So suppose H, this is the map on R square to R square, and this is an isometry. Then this will be an injective map, and we have some examples or some categories of isometries. So first we will have the identity map. So identity map, that is which is denoted by this. Identity of X is X, that is it fixes every element of R square. So this is an isometry, and similarly the negation of it, that is minus ID X, which is minus of X, that is which maps X to minus X. This is also an isometry. Whenever we hear the term isometry, be clear that we are discussing about some injective, distance preserving or non-preserving maps. Okay. The second category is reflection with respect to a line, which is denoted by like this SL. So suppose we have this line L in R square, then if we have a point, say V in R square, then how to get the reflection or the image of this point with respect to this line? What we will do? We will join this point to the line by making an angle 90 degree, and then we extend this line segment in the opposite direction and with the same distance, that is this V, and suppose this point is some point, say P. So VP is same as PSLV. Okay, and this line segment VSLV, this is orthogonal, or this is perpendicular to the line L. Okay, so this is reflection with respect to a line. Third category is rotation. So rotation with respect to a point. So say this is the point P in R square, and we want to find the rotation with respect to this point. Then how to do? Say this V is an arbitrary point in R square. So we need to find its rotation with respect to this point. So we will join this point V with the point P. So this is the line segment VP. And if we want to rotate it with respect to an angle theta in anti-clockwise direction, then what we will do, suppose this line segment PV is rotated by theta in anti-clockwise direction, and this V is like transformed to this R theta VP, that is rotation with an angle theta in anti-clockwise direction. With respect to the point P and this rotation of this point P. So this is rotation with respect to a point in R square. This is also in isometry in R square. Next category is translation. Translation means we are translating some elements. So suppose we have a fixed element V in R square, then we want to define translation with respect to this point. So suppose we have this map, TV from R square to R square, then how to define it? It maps every point X in R square or every element X in R square to X plus V. That is, we add this V to this. And obviously this X is, say, some x1 and x2 in R square, and we have this V as v1 and v2 in R square. And whenever we want to find the translation of x with respect to this V, then this will be x plus V. So this will be x1 plus v1 and x2 plus v2. So this is the form of translation of a point in R square. Okay. Next category is glide reflection. So this is actually composition of two isometries, that is TOR, translation and then reflection. So this one, like here we suppose this is the original position of some object or some point. Actually, like this will be some point, but to represent it properly, we are taking instead of some point P to this. Okay, so this is the initial position. First, we are applying this R. So this is like this. We are reflecting it and then we are translating it. So this will be the final position. So actually the transformation of this element is this one. And this is composition of two transformations or two linear maps or two isometries actually. Like composition of reflection and then composition of translation. And these five categories, these are the only possible isometries on R square. So whenever we have a given isometry on R square, that will fall either of these categories. Or we can say that any given isometry on R square can be obtained by composition of these 5 isometries. Okay. So let's understand this in some details. So what is reflection with respect to a line that passes through origin? So this is XY plane, and this is a line, say L, and how we define reflection with respect to this line. So this line L can be written like this. L is alpha per, which is the collection of all beta belongs to R square such that beta dot alpha is 0. That is, line L can be represented as the collection of all beta orthogonal to alpha. This is actually inner product of alpha and beta. Okay. So here what we are doing, we are fixing some element alpha. This is okay. Actually, the line is passing through the origin. So what we can do, uh, we can pick a point which has unit distance from the line, and this is making an angle 90° to the line. Okay, so this is how we can uniquely determine this alpha. And now what we do, mm, L is actually written by this alpha part. Now, this is a way to represent the reflection of a point. So suppose we have a point gamma in R square, and we want to find its reflection with respect to the line L. So this can be determined by this fixed vector alpha, and we can compute that S alpha gamma, that is reflection of alpha with respect to this, sorry, reflection of gamma with respect to this alpha. So this will be gamma minus twice of inner product of this gamma alpha over alpha alpha multiplied by alpha. Okay. Now you can also calculate that if gamma and alpha they are same, then reflection of gamma, this will be simply minus alpha, and if this gamma belongs to the line, then s alpha will be, sorry, s alpha gamma will be gamma, that is s alpha will work as the identity in that case. Okay, if you want detailed proof or explanation of these things, then you can refer the lectures by the course instructor. Here we are just summarize the topics, and then we will go to the question answers. Now, what is rotation by some angle theta about the origin? This is denoted by this r theta. Okay, so r theta of z, this is actually z e to the power I theta. Here this z is either this is an element of r square, or we can say this is an element of c, because r square and c, they are isomorphic. So okay, to find the matrix form of rotation, this will be helpful if we represent r square as complex plane. Why? Because every point z in the complex plane C can be written as x plus iy, and e to the power iota theta, this can be written as cos theta plus I sin theta. And whenever we multiply this z e to the power I theta, this will be x cos theta minus y sin theta plus I x sin theta plus y cos theta. So if we want to find the rotation by angle theta of some point z in C, then this will be z into e to the power I theta. That is, we multiply z by e to the power I theta. equivalently, we can say r theta xy. Now, okay, so actually this z is coming from complex plane and this xy, this is coming from r square. So corresponding to this representation in complex plane, we can get back to Euclidean plane again. And r theta xy, this will be, okay, what we do, like the first coordinate, this is x, and the second coordinate is y. So similarly, the first coordinate will be x cos theta minus y sine theta, and then second one will be x sine theta plus y cos theta. In matrix form, it can be written as cos theta minus sine theta, cos theta. Uh, this matrix multiplied by xy. So xy is the given point. So this is the way we represent a rotation. So whenever you want to find the rotation of a given point by some angle theta, what you will do, you will left multiply the point by this matrix. That is, like you will find cos theta and sine theta for the given theta, and you will compute this matrix cos theta minus sine theta, cos theta. And after the multiplication, you will get the rotation of the point xy. This is an important property in isometry of plane. So suppose we have an isometry on R square denoted by H, then there uniquely exists a translation T and H naught, which is an isometry that fixes origin. That is H naught 0 is 0. This is the meaning. Such that the given isometry H can be written as the composition of the translation and the isometry that fixes the origin. So any arbitrary isometry on R square can be written as a composition of translation and isometry. Okay. Now, suppose we have a map H from R square to R square, then we have some equivalent condition for H to be an isometry that fixes the origin. So uh, H is an isometry that fixes the origin, that is H0 is 0 if and only if HV dot HU is same as U dot V for any U and V in R square. That is, we can say that this isometry H, like if the map is isometry, then it preserves the inner product of any two element in R square. Okay. The third one is H is a linear map and there uniquely exists a matrix A from M to R. That is, A is a 2 by 2 matrix whose entries are coming from the real numbers, such that A transpose is identity matrix of order 2. That is, A is an orthonormal matrix. And HV can be written as AV. That is H of V, that is image of V under the map H. This will be same as the multiplication of V by A from the left side. Okay. So these are some equivalent conditions. That is, H will be in isometry that fixes origin if and only if it preserves the inner product, or H is in isometry fixes origin if and only if this is an R linear map and we have some orthonormal matrix such that HV can be written as AV. Okay. In general, we can write HV as AV plus W. Like, okay, so here actually in the theorem, we are taking H as an isometry that fixes the origin. But in general, if we take any isometry with the relaxation in this condition, then it will have the form this HV as AV plus omega, where this omega is again a fixed element in R square. Now, how to obtain the matrix A? Like whenever we have an isometry, say H, and H0 is 0, that is, it fixes the origin, then we can write HV as AV. But how we can get the form of the matrix A, which is orthonormal matrix? So how to do? So again, we consider the standard inner product, that is E1, which is 1, 0, and E2, which is 0, 1. And we assume that HE1, this is AB, and HE2, this is CD, because H is a linear map, we can say. And to get its form, it will be sufficient to find the images of E1 and E2. Then we can determine H uniquely. Okay, so we have HE1, which is AB, and HE2, which is CD. This is required. That is action of H on E1 and E2. Then HV can be written as X HE1 plus Y HE2. We put the values of HE1 and HE2, we will get this. HV is XA plus YC, comma XB plus YD, and this can be written as A, B, C, D in the matrix, and this is the point XY. So this matrix, whose rows are A, B, C, D, this is the matrix A. Now, this is an important conclusion that the collection of all isometries on the plane R square, this is a group. And what will be the group operation here? As isometries are maps, basically. So the group operation will be the composition of maps. Okay. This will be non-empty because identity map is trivially an isometry. And okay. Mm, how we define inverse in this? So suppose we have an isometry, then it will have a form like this, f of v as av plus w. Then its inverse will be defined like this. F inverse of v, this will be a inverse v plus f of z. Okay. So if we define the inverse like this, then the collection of all isometries under the composition of maps will form a group. Now we have some subgroups of the group of isometries of the plane. First one, which is denoted by O of R square, this is actually capital O. So this is the collection of all those isometries on R square which fixes the origin. Okay, so that is why we are like writing this O with respect to the origin. So this if we have all H from R square to R square such that H is isometry and H0 is 0, then this is a subgroup, and this is isomorphic to this. A belongs to GL to R such that AA transpose is I2, that is A is orthonormal. Okay, and okay, so whenever we have isometry, we can have a matrix A as we discussed. So that matrix must come from GL to R, that is the general linear group over R square. Okay, that is the group of all matrices of order 2 by 2 over R whose determinants are non-zero. But here we are taking this condition, that is AA transpose is I2. So determinant of A can be either 1 or -1. We will further see that if determinant is 1, then A is rotation. If determinant is -1, then this is reflection. Note that translation cannot come in this group of R square. Why? Because translation also translate the origins. Okay. Uh, we have, if we have T of V, uh, then it will map some x to x plus v. Then obviously TV of 0, this will be mapped to v. Okay, not 0. Okay, until unless v is 0. So translation by 0, that is trivial actually. So that is like the identity. So we are not talking about that. In general, translations cannot be an element of R square. It will have either rotation or reflection. But in both cases, it fixes the origins. So um, the rotation can be uh, a rotation about the origin. Okay? And the reflection will be a reflection that like reflection with respect to a line, but the line must passes through the origin. Otherwise, it will not fix the origin. Okay, so that's why we are fixing this. If we want to rotate, then the rotation must be about the origin. If we want to reflect it about mm, reflect it by a line, then the line must passes through the origin. The second group is this, the group of all translations. So as we said, like translations are not a part of the first category. So if we collect all the translations, then we will have another group. So we are representing it by T. So here actually we can say that TV of 0, this will be 0 if and only if V is 0. So this is the trivial translation. Or okay, what is T0? So T0 of x, this will be 0 plus x, that is x for all x belongs to R square. So this is the identity map actually. So identity map can be represented as a translation. Okay, so this set T is non-empty, and further with respect to the same group operation, that is the composition operation, we can check it is a group. So here the addition is defined by this, like translation of some point by u, and then we add the translation of the same point by v. This is the same of translation of the point by u plus v. Okay, that is tu plus tv. This is tu plus v. And how we define the inverse? So inverse of tu, this is t of minus u. Okay, which is actually like this. If we translate by u some point x, so we will get x plus u. And if we want to the identity here, what we will have to do, uh, we will have to again translate it by the negative. So this will be x plus u minus u, that is x. Okay, so this is the inverse. Now, this is the result. Suppose we have three distinct points in R square, which are not linear. So the points are P0, P1, and P2. And we have two isometries on R square, say F and G. And if we have this, that is F and G maps all these 3 points with the same images. That is f of p naught is g of p naught, f of p1 is g of p1, and f of p2 is g of p2. Then f and g, they will be same. That is, um, for two isometries to be same, this is sufficient that they map three distinct points to same points. Okay. Now, what are orthogonal maps? So let F is an isometry from R square to R square that fixes the origin. Then obviously, we discussed that we will uniquely have some A in GL to R such that AA transpose is I2 and F of E can be written as AV. Then we say that the map F, this is an orthonormal map. This is not orthogonal. Okay, so what are orthonormal maps? They are isometries and image of any V from R square will be AV, where this A is uh, orthonormal matrix on R square. Then we say that F is orthonormal map. And here we are taking AA transpose as I2 and this A is coming from GL to R, then obviously determinant of A will be either 1 or -1 because determinant of A and determinant of A transpose, they are same. So like this will be determinant of AA transpose, which is square of determinant of A, that will be determinant of A2, which is 1. And as we are working on R square, so determinant of A square is 1, that is determinant of A can be 1 or -1. Now, as we say that determinant of A, if this is 1 or -1, then the isometry F can be either reflection or rotation. So how to further classify? So consider the first case when determinant of A is 1, then A will have this form cos theta minus sin theta cos theta. You can check the determinant of A is 1. And in this case, if we write AV, so this will be like this is the matrix and this is the point. So this is actually V E I theta. We can check it. Okay, so this form is actually the rotation by angle theta, rotation of this point V. Okay, actually here this V has, okay, I'm writing it simply. V has this coordinates x and y. Okay, so if determinant is 1, then isometry is rotation. And if determinant is -1, then the isometry is reflection. Because in that case, the matrix will have this form cos theta minus cos theta. And one more thing, in both cases, the isometry fixes the origin. Okay, that is in this case, uh, if this point V is the point origin, then what will happen? If we rotate this point V by an angle theta, we will get AV, uh, this point. Okay, but if we consider this point origin, then the rotation will be the same. Okay, if we rotate it by some angle theta, we will get the origin again. Okay, and here uh, we are considering some line which is passing through the origin. And if we have some point, say this is V, and we want to find its reflection, then obviously like we are doing this. So this is perpendicular to this, and then we will extend. Okay, the diagram is actually not that much perfect. Okay, so actually, I want to do this. Okay, so this is the point V, and this AV, this is the reflection of this point about this line L, which is passing through the origin. So how to do this? We can again represent this in form of some metrics, and the matrix will be this: cos theta, sine theta minus cos theta. Now, what is the angle theta here? In case of rotation, we can simply consider what is theta. So actually, this theta is like whenever we join the point B, whose like rotated image we want to find. So we join this A to origin, and like then the anti-clockwise rotation that will give us the angle theta, which is represented in the matrix. But here in reflection, what we do, we consider this angle as like half of theta. So what is reflection? Reflection with respect to a line passes through the origin, and this line makes an angle theta by 2 with x-axis. So this is like mm, half of the angle theta, which is represented in the matrix form. Okay. Now, this is an important classification of isometries. So suppose we have an isometry like this, say f is from r square to r square, and f of v is av plus w, where w is some fixed point in r square. So if a is I2, that is, if this matrix A, this is the identity, then we say that the isometry is translation. If A is I2 and this point W, this is 0, then translation where the fixed, like, or you can say the point by which we are translating, if that is 0, then that will be the trivial translation, that is the identity map. Okay. So if the matrix is identity, we will have translation. And if the point is 0, then we will get identity, as we can see. Now, if W is 0, then again, W is 0, that is um, the origin is fixed under this isometry. Then again, we will have two sub cases. If the determinant is 1, we will get a rotation about the origin. If the determinant is minus 1, then we will get the reflection with respect to a line passes through the origin. Okay. And now if we relax this condition that W is 0, then in general, whenever we have determinant as 1, we will get a rotation. When we will have determinant as minus 1, we will get a reflection. Okay, so if determinant is 1, in general, that is omega need not be 0, then the rotation about a point P instead of rotation about the origin. So this point will be obtained by this. P is I2 minus A inverse and then W. Okay. And if determinant of A is minus 1, then and if we have this condition also that A omega is minus omega, then we will get a reflection. And if A omega is not equals to minus omega, then we will get a glide reflection. Okay. Now, what is dihedral group? So we have already discussed uh, dihedral groups are symmetries of regular polygons. So if we have this notation, D2n, which is sometimes represented by dn also. So D2n means dihedral group which has 2n elements, that is dihedral group of order 2n, and degree n. What is n here? This n is number of vertices in the regular polygon, or D2n means the group of symmetries of regular n-gon, we can say. Okay, so D2n can be represented by this. this is the collection of all isometries, but here the isometries are not the general one. Isometries which fixes the origin. So that's why we can write sigma, which are coming from O of R square. Okay. Uh, Such that sigma of n-gon is again n-gon because we are taking symmetries. Okay. That is, whenever we will transform the n-gon, we will again get the n-gon. Okay. And as we are taking sigma from O of R square, that is, we can have only rotation or reflection. So yeah, sigma can be either like either a rotation or a reflection by this. And we can also see that sigmas are bijection, obviously, and they map vertices of n-gon onto themselves. Otherwise, the symmetry will not be preserved. So if we find the action of sigma on the vertices, they can be find then we can find the form of sigma. Okay. For example, like if we have D8, then what does it mean? It means the symmetries of square in R square. Okay. Now we have some finite subgroups in OR square. First one is dihedral group. So its group representation can be written by this. Any element in D to N can be written as R to the power K, rho to the power L. Here R is rotation and rho represents some reflection. And K can vary from 0 to n minus 1 and L can vary from 0 to 1. Why? Because here this generating rotation, this is of order n, and reflection, this will have order 2 always. So whenever we will have a dihedral group, the generating reflection, that will have order 2. And what will be the order of the generating rotation? That will be same as the number of vertices in n-gon, or we can say the degree of the dihedral group. Okay. And yep, dihedral groups are generally non-abelian. If we take n is greater than or equal to 3, so this is another condition that R rho is rho R inverse. Okay, so whenever we have a group and we have two elements A and B belongs to G such that A is generated by this A and B, and this A is an element of order n and B is an element of order 2, and we have this condition that AB is BA inverse, then this group can have order at most 2n. And if it attains the order that is 2n, then it will become the dihedral group of order 2n. The another category is this. Sorry. Which is the cyclic group of order n generated by R2 pi by n. Here, R2 pi by n represents a rotation. A rotation whose order is n here. Or we can equivalently represent it by, like, this is the notation actually. So this is an important result. Whenever we have a finite group of OR square, then that will be either the cyclic group of order n, which is generated by a rotation, or we will have a dihedral group. Other than these two cases, we cannot have a finite subgroup of OR square. Now, consider some examples. So, as like this was the question, how we can classify the isometries. So Okay, we are considering some isometries on the plane R square. So this is the first. This is a question. We have this element. Okay, so okay. Here the matrix A is 1 by 2 minus root 3 by 2, root 3 by 2 and 1 by 2. And the isometry, which will be say F from R square to R square, that will be F of V as a V for all V belongs to R square. Okay, so this will be the corresponding isometry. So here we are representing the isometry by the matrix. Okay, so how to identify this? We have this. Okay, so we can see that the matrix is not I2, that is the matrix is not the identity one, so it cannot be translation. Now we need to check what is the determinant of A. Okay, what is the determinant? That is determinant of 1 by 2 root 3 by 2 minus root 3 by 2 1 by 2. So this is actually 1 by 4 plus 3 by 4, that is 1. So as determinant of A is 1, then this will represent a rotation. Then isometry is a rotation. Further, we can see that have any element W, that is W is 0. So this is the rotation about the origin. Further, uh, it is a rotation about the point, like if this is also asked, what is the point? About the point 0, that is the origin. As omega is 0 here. Okay. But you can also do this. What will be f of 0? F of 0 will be a0, which is 1 by 2 minus root 3 by 2. Root 3 by 2, 1 by 2. 0 is the 0 double, and this will be 0, 0 actually. Okay. That is A fixes the origin. Therefore, A is a rotation about the origin. Okay. Second question. Uh, Consider this element. So we have four conditions again: rotation, reflection, glide reflection, or anything else. Like this can be translation or identity one, obviously. So again, here the matrix is not the identity one. So this cannot be a translation. We need to find the determinant of A, which is determinant of 1 by 5 minus 3, 4, 4, and 3. So this is -1 this time. Okay. Therefore, A is a reflection, and this is with respect to the line passes through the origin. Why? Because omega is again 0 here. Okay, so option B is correct. Come to this. The only isometry of R square fixing the origin and the standard basis is the identity. So the statement, whether this is true or false. So let, we are writing F. Let F from R square to R square an isometry such that f of 0 is 0, that is, it fixes the origin, and f fixes the standard basis, which is E1, E2, or 1, 0, 0, 1. Okay, that is f of E1 is E1, f of 1, 0 is 1, 0, you can say, and f of E2, this is E2, or f of 0, this is 0, 1. Okay, then what we want to do, we want to check whether this f can be other than identity or not. So what is our claim? That f is the identity on R square. That is, f of v is v for all v belongs to R square. Okay, so remember this result. H is an isometry that fixes the origin if and only if it preserves the inner product. Okay, so since F is an isometry that fixes the origin, preserves the inner product on R square. That is f of a inner product of fu and fv. This will be same as inner product of u and v for all u and v belongs to R square. Now fix u and vary this v for the basis elements. That is, if we consider v as even and what we will get fu f even. This will be u dot even, which is same as fu dot even, and this is u dot even. Why? Because f even is even. And similarly, fu fe2, this will be ue2. So this will give us fu dot e2. This is u dot e2 because f fixes the second basis element e2 as well. Okay, now u belongs to R square can be uniquely written in terms of even and e2. Actually, a unique linear combination of even and e2. You can see from linear algebra because even and e2 are basis elements. So u is c1 even plus c2 e2 for some c1 and c2 belongs to R. Then what will be fu? Fu will be f of c1 even plus c2 e2. That is c1 f even plus c2 f e2, which is same as c1 even plus c2 e2. But this is actually the value of u. F u is u for all u belongs to R square. Therefore, F is the identity map. The answer is true. There cannot be a non-identity isometry on R square that fixes the origin and the standard basis as well. Okay. Now consider this question. We have a map from R square to R square defined by this, and we need to check whether this is an isometry of the plane or not. Given h from R square to R square such that hxy, this is x plus 1, y plus 2. Check whether H is an isometry on R square. So how to check it? A map will be isometry if it is distance preserving or if this is norm preserving. Like how we define the isometry initially. Okay, this one. H will be isometry if and only if norm of H u minus HV, this is norm of u minus V, or the distance between HU and HV, this is the distance between U and V. And how we find the distance in R square? So this is the way. So just use it and solve the question. So consider 2 points. X1, Y1 and X2, Y2 in R square. What will be distance between X1, Y1 and X2, Y2? Square root of x1 minus x2 square plus y1 minus y2 whole square. And what will be the distance between h x1 y1 and h x2 y2? That is the distance between x plus 1, x1 plus 1, y1 plus 2, and x2 plus 1, y2 plus 2. So this is square root of x1 plus 1 minus x2 plus 1 whole square plus y1 plus 2 minus y2 plus 2 whole square. So yes, this is square root of x1 minus x2 whole square plus y1 minus y2 whole square, which is actually the distance between x1, y1 and x2, y2. Therefore, H is an isometry on R square. Okay. So, yep, this is an isometry, but which kind of isometry? So, again, H of x, y, this is x plus 1, y plus 2, which can be written as x, y plus the point 1, 2. So, H is a translation by this point 1, 2 belongs to R square. Okay. So whenever an arbitrary map is given on R square and it is asked to check it is in isometry or not, what you will do, you will find the distance between 2 points and then distance between images of those points. If these two distances are same, then you would declare the map as an isometry on R square. Okay. Now come to this. Verify whether this is an isometry of the plane or not. So given h from R square to R square such that hx5, this is x plus 5 comma 0 for all x and y belongs to R square. Okay, so consider these 2 points. 0, 0 belongs to R square and 1, 1 belongs to R square. What will be their images under this map? So at 0, 0, this will be 0 plus 0 comma 0, that is 0, 0 again. That is, yep, it fixes the origin. And what is h1 comma 1? Is 1 plus 1, that is 2 comma 1. Okay. Now, the distance between these points 0, 0 and 1, 1, this is square root of 0 minus 1 whole square plus 0 minus 1 whole square. That is square root of 2. But between their images, distance between h00 and h11, that is distance between 00 and 21, that is square root of 0 minus 2 square um, wait, the second one will be 0 now, so this will be 2 comma 0. Okay, minus 0 minus 0 whole square, so this will be 4. We are taking the positive sign because we are in that this d is distance and distance are positive. Okay. So we can see that distance of 0, 0 and 1, 1, this is not the same as distance between h00 and h11. That is, the map h is not distance preserving. That is, h does not preserve the distance in R square. Therefore, H is not an isometry. So here actually you see that I'd like to mention that hx5, this is x plus 5 comma 0. So here the second coordinate, this is 0. So the map is not surjective. Okay, H is not a surjection. So that is how you can see, like this cannot be a bisection, and it will have some uh, difficulty to be in isometry. And yep, it fixes the origin. So that's this is an into map. So this cannot be in isometry. Okay, we have a given map, and we are to check whether this is a rotation about this origin through an angle pi, 3 pi by 2, or anything else. So do it. The given map is T, which maps every element A, B of R square to minus A minus B. This can be alternately written as TAB is minus A minus B. Okay. So first we need to check whether this is an isometry or not. So let's check whether this is distance preserving or not. So the distance between T of A1, B1 and T of A2, B2, this is the distance between minus A minus B, okay, minus A1 minus B1 and minus A2 minus B2, which will be the square root of minus A1 plus A2 whole square plus minus B1 plus B2 whole square, which is square root of uh, A1 minus A2 whole square plus B1 minus B2 whole square, which is actually the distance between A1 B1 and A2 B2. So the map T is an isometry. Now check what is the category of this isometry, like whether this is a rotation, reflection, or anything else. The determinant of we need to consider the determinant of the corresponding matrix A. And how to form this? For that, we need the images of the standard basis elements, that is T of E1 or T of 10, which will be minus 10, and T of E2, that is T of 1. This is 0, minus 1. Okay. Now, how we form the matrix A? This matrix will be TE1, TE2. That is, we write the images of E1 and E2 in columns, and thus we get a matrix correspond to this isometry T. So A will be minus 1, 0, that is TE1, and then 0, minus 1, which is TE2. And what will be the determinant of A? This will be the determinant of this matrix, minus 1, 0, 0, minus 1, which is clearly 1. Therefore, T is a rotation. Also, see, what is T00? This is 0, 0. By the definition of the map, it means T fixes the origin, or we can say the corresponding vector omega, that will be 0 in this case. Okay, so T is a rotation uh, okay, so these are the options, like whether this is a rotation about the origin or about any other point. So as the rotation fixes the origin, so this will be a rotation about the origin. Okay. Now we need to find the angle of rotation. So consider this matrix. Okay, so come to this as we need to compare. So, okay, this is the matrix in the case of rotation. So the matrix is cos theta minus sine theta, cos theta. So if we compare our matrix with the standard form, what we get, cos theta is -1 and sine theta is 0. Okay, so this will be the correct option. That is, we have a rotation about the origin through angle pi. Therefore, theta is this. T is a rotation about the origin through. Okay. This is the next question. We have another map given by this equation, and again we need to check the type of it. The so okay. The given map is AB. This is by root 2 times A minus B, A plus B. First, we will check whether T is an isometry. Distance between T of A1, B1 and T of A2, B2. So for this, what we are doing, we are taking these 2 points, A1, B1 and A2, B2 in R square. Okay. So what is the distance between their images under the map T? This will be distance between 1 by root 2 times A1 minus B1, or let's write it in row form. So this will be A1 minus B1, comma A1 plus B1, and 1 by root 2 A2 minus B2, comma A2 plus B2. Okay, so this will be the square root of root 2. You can take it common, and it will be A1 minus B1 whole square minus A2 minus B2 whole square. So this will be minus B1 minus A2 plus B2 whole square plus 1 by root 2 A2 minus A1 plus B1 minus A2 minus B2 whole square. Okay. So this will be the square root of 1 by 2, and this will be A1 square plus B1 square plus A2 square plus B2 square minus 2 A1 B1 plus 2 A2. Okay, so this is 2 A1 A2 with minus sign plus 2 A1 B2 plus 2 A2 B1 minus 2 B1 B2 minus 2 A2 B2 plus simplify the second term. So this will be A1 square plus B1 square plus A2 square plus B2 square plus 2 A1 B1 minus 2 A1 A2 minus 2 A1 B2 minus 2 A2 B1 minus 2 B1 B2 plus 2 A2 B2. Okay, so this is same as the square root of half of 2 A1 square plus 2 B1 square plus 2 A2 square plus 2 B2 square minus, okay, so these terms will be cancelled out. This will be minus 4 A1 A2 and minus 4 B1 B2. Okay, so this can be written as the square root of A1 minus A2, or fine. This is like A1 square plus A2 square minus 2 A1 A2 plus B1 square plus B2 square minus 2 B1 B2. So this will be the square root of A1 minus A2 whole square plus B1 minus B2 whole square. So this is the distance between A1 B1 and A2 B2. So by this, we can conclude that T is an isometry. Okay. Now again, we compute the corresponding matrix A. For that, we need the action of T on the standard basis elements. That is what is TE1 or T10. So this is 1 by root 2 A minus B and A plus B. That is 1 by root 2 A minus B, that is this, and 1 by root 2 A minus B. So this is A plus B. Okay, this will be this. And similarly, TE2 or T01, this will be 1 by root 2 A minus B, that is minus 1, and 1 by root 2 times A plus B, that is simply this. Okay. Therefore, the matrix A, this will be a matrix formed by TE1 and TE2 column wise. Okay, so this is matrix 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. Now, what is the determinant of A? This is the determinant of 1 by root 2 minus 1 by root 2, 1 by root 2, and 1 by root 2. So this is 1 by 2 plus 1 by 2, that is 1. So T is a rotation. And the action of T on origin, this is 1 by root 2, A plus B, A, A minus B, A plus B. Okay, so this will be same 0, 0. Therefore, T is a rotation about the origin. Okay. Now we need to find the angle of rotation. So again, this will be cos theta and this is sin theta. Theta is an guided directly. Cos theta is 1 by root 2 and sin theta is 1 by root 2. Therefore, theta is pi by 4. Thus, T is a rotation about the origin at the angle pi by 4. Okay, the next question, if T be an isometry, then AT, where this A is some element from R. This is an isometry if and only if A is dot dot dot. So we need to find the value of A such that AT will again be an isometry. If T is an isometry. So how to do it? Since T is an isometry as given, what we have, norm of T of again A. Okay, so X minus T of Y. This is norm of X minus Y. Here, X and Y are coming from R square. Now, AT is an isometry if and only if norm of ATX minus ATY. This will be same as norm of X minus Y for all X and Y belongs to R square. So this is equivalent to AT is an isometry if and only if norm of A of, okay, so this can be written as A of T of X. Okay, so this will be, we can take A common and this will be T of X minus T of Y. This will be same as the norm of X minus Y. This is equivalent to this. Since norm of X, this is mod A norm of X. Okay. But we know that norm of Tx minus Ty is same as norm of X minus Y. So this will be true if and only if mod of A is 1. Okay. Where this A is coming from R. And what will be the values of A in R if the modulus is 1? So this is if and only if A is either 1 or minus. So here what we will have plus 1 and minus. Next question. Consider T from R square to R square given by this definition. Then T is reflection about the line y equals to x, or reflection about the line y equals to minus x, or this is a reflection about the x-axis, or the reflection about the y-axis. Okay, to do it. And that T from A B, this is minus B minus B, or AB belongs to R square. Since the distance between P of A1, B1 and P of A2, B2 for any two elements A1, B1 and A2, B2 in R square, this is the distance between minus B minus B1 minus A1 and minus B2 minus A2. This is the square root of minus B1 minus plus, so this will be plus B2 whole square plus minus A1 minus of minus A2, that is plus A2 whole square. So this is the square root of A1 minus A2 whole square plus B1 minus B2 whole square. Okay, so this is the distance between A1 B1 and A2 B2. Okay, it means T is distance preserving. So T is an isometry. Now, what are the images of TE1 and TE2? So this is minus B minus A means 0 minus 1. And second one, that is TE2. This is T01 means minus B means minus 1, 0. Therefore, the matrix A, this will be TE1, TE2, that is 0 minus 1, minus 1, 0. We can see that the determinant of A, this is minus 1 this time. Okay. And this is the matrix A. Now, let's compare it with the standard form. This one. If the determinant is minus 1, and the matrix A is cos theta, sine theta minus cos theta, then we have a reflection about a line passes through the origin. This is actually the this is corresponding to the case when the isometry or the reflection preserves the origin. Okay, then the reflection will be with respect to the line passes through the origin, and it will make the angle half of the angle appears here. Okay, with the x-axis. So we conclude here that A is a reflection, is the first conclusion. Also, P of 0, 0. So this will be minus B minus A. So this will be the origin again. That is T preserves the origin. Okay. So till now, what we have concluded that T is a reflection with respect to a line passes through the origin. Okay? But uh, we need to find the line. Okay, so it will be sufficient to know what is the angle this line makes uh, with the x-axis. Okay, so for this we need to compare this matrix with the standard form. Here cos theta is 0 and sin theta is -1. Where theta by 2 is the angle. The line makes with the x-axis. Okay, so what is theta? Okay, and then we will take the half of that to find this. So this will be p pi by 2. Okay, uh, theta by 2 is 3 pi by 4. So this is the angle, this is the angle this line makes with the origins. Okay, so what will be the line actually? The line will be something like this. Uh, this is our x-axis, y-axis, and now line passes through the origin and it makes angle 3 pi by 4 with x-axis. So the line will be this one. Angle. This is 3 pi by 3, which is actually theta by 2. Now, what is the line? The line is clearly we can see this y equals to -x, or we can determine its form using the standard form of lines and all. So this is a clear geometrical representation for the conclusion. So what is the answer? P is the reflection with respect to the line passes through the origin making uh, theta by uh, 2 means 3 pi by 4 angle. So this is about the line y equals to -x. 3 pi by 4. Or the line y equals to -. Okay, so this is the correct. That's all for today's session. We will meet in the next session upcoming. Thank you.